When a new pattern or practice, a new library or feature arrives on the scene, the first instinctual thing we as developers do is rush to see what we can build on top of it. What element of our workflow is directly improved by this new feature or library? What does it make possible? How does it reimagine problems we thought we had already solved? But this vertical integration is not the only rubric on which we should judge new features. We shouldn't judge new features based just on what we can do with the closed set of features that library, for example, comes with. There's another dimension to the problem. How can we widen the base of that library? How can we widen the base of that feature? And in accordance with this formulation, in the previous 2 years, I gave talks about the networking TS where I talked about how we could integrate with it vertically, how we could take the features that come out of the box, build on top of those, and use them to build powerful, expressive applications. Now, this year, I would like to loop back and examine something more nuanced and complicated, but just as essential. How can we widen the base of the networking TS? How can we author entirely new I/O objects that stand beside the networking TS as a fully integrated, consistent part of that ecosystem? But before we jump into that problem, let's talk a bit about the status of the networking TS itself. Just as in previous years, the networking TS is blocked on executors, the paper P0443. For those of us who want to use the features of networking, this might seem annoying. It might be frustrating that we can't just use networking. Maybe we don't directly care about executors. But is that really true? One of the things that asynchronous operations do is they schedule work to run in the background. This is, in fact, exactly how they signal that those operations have completed. It's what makes them asynchronous. And this is exactly the problem the executor's effort sets out to solve. And so if the committee were to standardize networking before executors, we may end up with two divergent or conflicting ways of solving exactly the same problem, which wouldn't be very healthy for the ecosystem. And so we should be happy that the committee is holding back a bit, happy that we're going to get a consistent integrated ecosystem, happy that hopefully, all things going well, notwithstanding even more black swans in our already tumultuous universe, networking and executors will land in C++23. But if you do want to use executors and networking today, or at least use what we think they'll look like when they land in C++23, you don't need to wait. You don't need to despair. Because these are library-only features, and Boost ASIO and its standalone version, which is not part of Boost, ASIO, ship these features today and have been shipping various versions of these features for over a decade. And so if you want to use those features, just download ASIO or standalone ASIO. This is, in fact, exactly what I've done to prepare the code samples on these slides. I've used the very latest version of ASIO, which allows me to demonstrate the pathway forward for integrating networking with P0443, something that I'll touch on later in the presentation when the opportunity arises. Now let's move to the networking TS itself. Actual code written with the networking TS, the things we can actually do with it. Let's look and see what we did in previous years and see if we can find the hole we're going to fill this year. 2 years ago, I introduced this sequence diagram. I introduced this asynchronous operation, async wait, then write, which does exactly what it says on the can. It waits for some amount of time and then writes some number of bytes. The initiator, the person who kicks the operation off, gets the ball rolling with async wait, and then his or her lifetime abruptly ends. This is definitional of asynchronous operations. If the initiator was waiting around for the completion, it would be a synchronous operation, not an asynchronous operation. The timer then proceeds in the background until it posts to an executor. An executor, as we discussed in previous years, is a handle to an execution context, some place that our submitted function objects can be invoked. And in accordance with this formulation, there is thereafter the invocation of a function call operator of a completion handler, a function object which handles the completion of an asynchronous operation, in this case, async wait. But waiting isn't all we're setting out to do. We're setting out to wait and then write. And so this isn't really a final completion handler, it's an intermediary. Its job is to layer on top some higher level logic and implement the entire asynchronous operation. And so this intermediate completion handler turns around and kicks off async write on a socket or some other kind of stream. Now, async write itself is made up of parts. It's made up of 0 or more calls to async write sum. And so these proceed until all the bytes are written or there's some error condition, there's a post to an executor, and then the operation finally ends. This pattern of bringing together higher level logic from smaller parts is what we studied in the previous 2 years. We learned about composed asynchronous operations. We learned how we can iteratively construct higher and higher level asynchronous logic until eventually, maybe, we can implement our entire application as one invocation of one highly generic, highly reusable, testable initiating function in main. And the techniques we used to accomplish this were, first and foremost, templates and named type requirements. To obtain the kind of generic code that we would need. We can't write truly generic code if we're married to sockets and timers of concrete types. And so instead we took a step back and realized that we didn't care that we were actually working with a socket. All we cared was that we could write some number of bytes. We didn't care about the socketness, we cared that it was an async write stream. And so we leveraged generic programming to get the benefits of polymorphism and static typing. But to increase the flexibility and power of the ecosystem even further, that's not all we did. We deferred to customization points laid out by the networking TS, which allowed our users to inject their concerns, which saved us from having to make arbitrary decisions on their behalf, decisions which were practically guaranteed to be incorrect. For example, writing some bytes says nothing about parallelism or synchronization. But because at the end of the operation, we're going to need to submit some work for background execution, we're stuck in this quagmire where maybe we have to make a choice about parallelism and synchronization, but at our level of analysis, our level of context, we don't know which decision to make. And so the networking TS provides us with mechanisms for allowing users to make those decisions for us. In this case, rather than going off and choosing some execution context for the user's final completion handler, we defer to the executor association that completion handler carries with it, which customizes the means by which that completion handler is invoked at every level, which allows the user at the top level, knowing all their requirements, seeing the whole application, to inject their requirements regarding parallelism and synchronization down to us, so we don't need to make that decision. But we already knew all this. We studied this in the previous 2 years. So where's the hole in our understanding? What are we trying to fill in this year? Let's take another look at that sequence diagram. After the review, we now understand that it's within our power, within our knowledge, to implement this entire operation. We can string together the constituent parts and project the operation upwards to the next level of consumer in the stack. And carrying on with this, we could implement async write. We have the power to string together 0 or more calls to async write sum. But what about async wait? What about async write sum? They're just presented as black boxes, as atomic, taken for granted bits of functionality that ship with the networking TS. How could we build one of these? How could we build the baseline asynchronous operations that our formulation of composed asynchronous operations depends on? After all, composing asynchronous operations is useless if there are no asynchronous operations to compose. And while you can reflexively compose composed asynchronous operations, at some level of analysis, you're going to reach the bottom layer. You're going to need to bootstrap all these guarantees and practices from nothing. And indeed, if you think about this formulation in the context of what we did in previous years, you'll realize that while our operations did pass through guarantees of the networking TS, they did abide by its practices. What they didn't do is establish those from the most basic level. For the executor association I discussed earlier, we simply wrapped the user's completion handler. We simply passed through their executor association. And then we took our intermediate completion handler and passed it down to the next layer. If it wasn't for the fact that next layer actually synthesized those guarantees, actually honored that association at a baseline from nothing, we would not actually have passed through the guarantees and practices of the networking TS. We were relying on the baseline layer establishing that for us. But now here we are, seeking to implement the baseline layer. We're seeking to implement our own I/O object, which exposes totally new asynchronous functionality in the context of the networking TS. The TS, of course, ships with some of these. They are the baseline of its asynchronous toolbox. For example, stdnet IP TCP socket and studnet steady timer are I/O objects. But this is not an exhaustive closed set. We can imagine new asynchronous functionality we might want. In the financial domain, for example, we may wish to write an asynchronous socket, which uses EFEI. Or in other domains, we may wish to have an asynchronous database access layer. Or maybe, just maybe, you want to asynchronously spool out a few pages to be printed on that LaserJet printer across the office. Now, each of these possibilities is compelling and interesting, but one of the things they all have in common is they involve vendor or operating system specific functionality. And that's not the purpose of this talk. This isn't a POSIX or a Windows talk. This is a C++ talk. So what I'd like to do is extract out what's common to these three possibilities, extract out what's necessary to integrate them into the framework of the networking TS. And that is the suspension of a completion handler at the initiation of an operation. When you go to spool that piece of paper to be printed out from the printer, you need to take the completion handler and you to put it to sleep. And when that print job is finally fully spooled, you need some way to resume it, to invoke it and let your user know that they can head across the office to pick up their printed pages. What you need, if you think about this in its analog in the synchronous world, is a condition variable. And so we're going to write an asynchronous condition variable as a means of introducing the patterns and practices of writing I/O objects in the networking TS. Our I/O object, our asynchronous condition variable, our basic async event class, will of course have a type alias to expose its template parameter, the executor that it will store and use internally. And then it will of course have a unary constructor to take in this executor and construct itself, and a get executor member function to return that executor. Note that in some conceptions, this nullary invocable get executor member function is actually definitional of an I/O object. If it has this member, then under this definition, it is an I/O object. Then we pull in those familiar methods from condition variable, notify1 and all, which variously cause the completion of 0 or 1 or 0 or more asynchronous operations. And then we have the star of the show. We have the initiating function from our baseline, from scratch, asynchronous operation, async wait. Now, if you think about the formulation and motivation for this class, for this example, it was around suspension and resumption of completion handlers. And indeed, that's all this class does. Which raises the question of how do we store those completion handlers? What do we actually do with them when we suspend them? And how do we resume them? And if we try and think about this in terms of previous years, we once again find that we were just kicking the can down the road. In previous years, we took in and deduced a user's final completion handler, but then we just wrapped it up in our own intermediate completion handler, and then provided this intermediate completion handler in turn as the completion handler for a lower level operation. The suspension and resumption of that completion handler was out of our hands. It was the responsibility of that atomic black box lower level that we didn't understand and didn't think about. But now, this year, that can we kick down the road is rolling up at our feet. Because we're positioning ourselves at that lowest level. We're trying to bootstrap asynchronous functionality from nothing. And so, given that the completion handler could be of any type, we need to figure out a way to store an invocable object of any type. The first thing that might come to mind is std function. But std function is not fit to task, because std function requires that its target be copyable, whereas the networking TS only mandates that completion handlers be movable. What we need is something like any invocable, previously known as unique function. But we also need something more. We need something that wraps up some of those guarantees and practices of the networking TS that we need to bootstrap from nothing. We need to take care of some of this nuance and see exactly what we're getting ourselves in for by diving down to the very lowest level. And so we're going to author this pending unary class template. Note that much like stood function, it has a primary class template, which is declared but never defined. And it then has one specialization for when the sole type provided as a template parameter is a function type. This specialization has two members, a unary constructor, which type erases its argument, and a function call operator, which invokes the target. But that's not all, because that simple formulation fails to encapsulate that requirement, that guarantee of the networking TS that we should honor. And that, if you remember from last year, is that completion handlers carry around with them not just an associated executor, not just an associated strategy for invoking callable objects, but also an associated allocator, a means by which they would prefer the asynchronous operations to which they're submitted to allocate memory. And so we can see in the comments that the unary constructor, rather than using new to allocate memory for the type erasure, uses the associated allocator. It allocates storage using that allocator and then forwards the T into that storage. And then when we examine the function call operator, we come across another nuance of the networking TS. And that's that the networking TS would really like it if before the up call, before we invoke the completion handler and indicate our operation is finished, we deallocate all of the memory we allocated through the user's associated allocator. If you think about it a little bit, this actually makes perfect sense. Because if you need some resources to perform a task, let's say you need to allocate some memory, if you aren't done with those resources, if you haven't released them, you're not really done. And so why are you going off and invoking a completion handler when you're not done? And so rather than just invoking the target in place, our function call operator will take the target and move it onto the stack, get its associated allocator and deallocate the storage, and only then perform the up call, only then invoke the final completion handler. Note that if you want the fully worked version of this class, which I've elided in the sake of space and time, you can go to the example code that's associated with this talk. There's a fully worked and tested version of this slide. With this in hand, we can now take a stab at implementing our I/O object. We can take a stab at synthesizing asynchronous functionality from nothing. We can fill in the body of basic async event. Of course, we're going to store that executor we accept as an argument to our constructor, and then we're going to have a vector of these pending objects, a place to store each and every completion handler for each and every outstanding asynchronous operation. We're going to have a totally banal implementation of our unary constructor, which simply moves the executor into the storage that we provided for it. Then we have an equally banal implementation of getExecutor, which just returns that executor. And we have a fairly standard implementation of notify1. If there are any pending completion handlers, if there aren't any pending completion handlers, we return 0 because there's nothing to do. Otherwise, we move out the first such completion handler. We pop it out of the vector to make sure we don't leave something lying around in a move from state in the case of exception. We invoke the completion handler and we return 1, signifying that one asynchronous operation was completed. Note that the implementation of notify all has some complexity if you want to achieve both efficiency and exception safety. And at any rate, that's not really the topic of the talk, and so I've elided it. Which brings us to that all-important member function, which brings us to the implementation of async wait. We take in a completion handler and we grab its associated executor, providing as a fallback the default candidate object, the executor that we store in our cells. This is because we need to bootstrap that executor association from nothing. We need to make sure to go off and honor it. Then we package up the user's completion handler and the executor, and we emplace into the pendings. We suspend the completion handler. We allocate storage for it and put it to sleep. Once it's resumed inside a call to notify one or notify all, we go off and we grab the allocator associated with the user's completion handler, because we need to honor that requirement as well. Then we use dispatch on the executor, providing the handler and the allocator, to make sure we're honoring the user's execution requirements. Remember, This invocation is taking place below notify one or notify all on the call stack. And we don't know anything about the environment from which the user is calling notify one or notify all. And therefore, we need to be very careful to go out and make sure we honor their execution requirements. We need to give their associated executor an opportunity to invoke that work rather than invoking it wherever we ourselves happen to be invoked. But there's an issue with this example. And the issue with this example is that we're not actually honoring all the requirements of the TS. We've forgotten about something that was introduced 2 years ago, about completion tokens. The mechanism by which the networking TS allows callers to customize the mechanism by which they're notified of completion, which allows them to divorce themselves from raw completion handlers and use things like promises and futures to receive the status of their asynchronous operation. And the reason that's been elided is because in previous years, we used boilerplate regarding async result and async completion to obtain a return value and a final completion handler. And that's changed in the intervening year because there's something new on the scene, which not only takes care of this boilerplate, but also enables a powerful new use pattern. Because the networking TS, or at least SG4 has kind of green-lighted this, and ASIO include this new functionality called async initiate, a function template which takes in 2 or more arguments, an initiation, which is a callable object that encapsulates all of the logic of beginning the operation, and then the completion token it's going to use to learn about the completion handler and return type. Note this return type is the deduce type that it returns, and then trailing arguments, which will be decay copied and forwarded through to the initiation. The initiation receives as its first argument the completion handler, and then as subsequent arguments, all of these arguments. This gets rid of all this async result and async completion boilerplate and makes implementing asynchronous operations a lot cleaner. I don't know about you, but pretty much every time I had to actually bootstrap completion token handling, I had to actually go and look at the documentation in order to figure out how to write it, whereas this just writes itself. But perhaps even more exciting is the fact that async initiate actually opens up a totally new use case, exposes a totally new workflow. Because previously, the initiation of operations in the networking TS was eager. When you called the initiating function, by the time it returned, the operation was pending, outstanding, and executing in the background. And that's fine when you're using promises and futures. That's fine when you're getting notified of completion by way of a completion handler. But what happens if you're using something more esoteric, like senders and receivers from P0443, or coroutines, which were found to actually mesh up with this paradigm so poorly that using it required the allocation of a mutex to synchronize between the initiation, possible completion, and suspend resume cycles of the coroutine. And so async initiate doesn't necessarily just invoke your initiation right away with the completion handler and arguments. Instead, it provides the implementer of the completion notification mechanism with a way to capture and suspend the initiation, to defer it to be invoked lazily later. And while this opens up a lot of power, it opens up a lot of new workflows. It comes with a sharp edge regarding those trailing arguments. I said before, those trailing arguments are decay copied and forwarded, which means that actually they will be treated as value types. Copies or moves may occur. And so if your initiation requires one of the parameters to the initiating function by reference, you need to be sure to capture that by reference by capturing it in the initiation. You can't launder it through these trailing arguments and hope that it will just work, because it probably won't. Now that we've learned that, let's go back and modify our initiating function so that we actually honor this requirement of the TS, so that we open ourselves up to notifying our users of completion in any way, not just via completion handlers. The first thing we're going to do is we're going to take and indent all the code we had before and put it inside a lambda, which will be our initiation. That lambda accepts just one argument, which is the completion handler, deduced by async initiate from the completion token, which is passed as the second argument to async initiate. Notice that because completion tokens may also synthesize return types to be returned from the initiating function, we return whatever async initiate returns. Then we need to go off and we need to tweak our signature a bit. We can't just return void. We need to return whatever async initiate does, and so we return decal type auto. And then we're not trafficking in completion handlers anymore. We're trafficking in completion tokens, and so we rename the appropriate template argument and parameter to the function. But this isn't all, because if you look at where we dispatch into that executor, You'll notice that's networking TS style executors. The networking TS provides this triplet of ways of submitting work to an executor: defer, dispatch, and post. But how does P0443 do it? Well, it doesn't do it that way. Because what was noticed in the executor's effort was that defer, dispatch, and post do encapsulate useful and valuable semantics for submitting work, but they don't capture all the possible semantics someone might want. There are innumerable such semantics, and those semantics are, in some sense, all orthogonal from each other. And so the user may wish to establish any combination. And so if we were to give each such combination of semantics a name, like we do with defer, dispatch, and post, we'd wind up with a combinatorial explosion in the number of functions that have to be provided to support all such semantics, which is clearly unacceptable. And so in P0443, there's one true way to submit work to an executor. The customization point stood execution execute, which you invoke providing the executor as the first argument and the work to submit as the second argument. Which leaves on the table the question of, how do we establish those semantics? How could we re-implement the contracts of defer, dispatch, and post? Well, the way P0443 imagines this is by using a mechanism called properties. Rather than an executor just being a handle to an execution context, an executor remains a handle to an execution context, but also encapsulates a set of semantics by which it submits work to that execution context. These semantics are established by so-called concept-preserving operations, prefer and require. That is to say, when you pass prefer an executor, it returns you a new executor, possibly of a new type, still an executor, possibly with certain semantics established. Whether the semantics are actually established or not depends on whether you prefer or require them. As an example of using this, if you wish to re-implement post, you would require blocking.never, since one of the semantics of post is that post will never await the invocation of the function object. It will not block. And then as a hint, which I'll not really get into here, a scheduling hint to the execution context, you also prefer continuation.fork. Once those concept-preserving operations return you an executor which appropriately encapsulates those semantics, you can use stood execution execute to submit that work. So let's go back and modify our example to bring it in line with P0443. Much of it looks the same. We still go off and get the associated executor, and we still put the work to sleep, and we still defer to the completion token machinery in the form of async initiate. But once we grab that associated allocator, things start to look different, because now there's no dispatch function to pass that allocator to. Instead, the fact that we want our executor to allocate memory with that allocator becomes a semantic requirement, something we establish through the properties system. And so we prefer that the executor allocate memory with that allocator by attempting to establish the stood execution allocator property on it. Note this is a preference because you can conceive of executors which don't ever allocate memory, and because the networking TS does not necessarily make allocator associations as binding as executor associations. Once we have back this new executor, the new executor with our semantics established, we can submit it for execution by calling stood execution execute, passing the executor and the handler. And so now finally, we've fully worked through our example, brought it in line with P0443, and supported any completion notification mechanism. Which brings us back to the initial question we set out to answer. How do we store users' final completion handlers? Have we succeeded in that task? Let's review what we've actually done. We have this pending type erasing wrapper, which type erases the user's completion handler. And therefore, it owns the user's completion handler. It is, in turn, owned by a vector of such objects. And that vector is resident in our I/O object, and so our I/O object owns that vector. Transitively, this means that our I/O object owns the targets. It owns the type erased completion handlers. But this is all type erasure. This could all involve any type. And when we say any type, we mean it could have any members. And one of its members could be the I/O object itself. One of its members could transitively own the I/O object. This would introduce an ownership cycle, a cycle that would not be broken unless the pending is invoked, unless it moves the object onto the stack and allows its lifetime to end. But this formulation would require that every asynchronous operation always complete in order to ensure all resources are cleaned up. And we don't live in a world that's anywhere near that perfect. Users sometimes just walk off on whole asynchronous components, allow their lifetimes to end, and move on with their lives. And it would be wholly inappropriate for us to leak memory in this instance. So, what can we do? Well, we could just ban it. We could just document the fact that users aren't allowed to do this. We could tell them, if you have such an ownership cycle and you call my initiating function, whatever happens is your fault. You take responsibility for it. The Restinio library, which is built on top of Asio and which implements a REST server, does exactly this. In its documentation, it tells you that if you attach handlers to its connection objects, which transitively own that connection object, that's a memory leak, and Restinio accepts no responsibility for what happens to you. But we're establishing the baseline of asynchronous I/O for standard C++ in the networking TS. And if you look through TS code or just think about it, you'll realize this is a useful pattern. If you have a state for a connection, that connection state should probably contain the sockets and timers that are associated with that connection. And all the completion handlers floating around implementing the logic associated with maintaining that connection should probably have some say in the ownership of that connection. They should probably be able to keep it alive. But this is exactly the ownership cycle I just laid out. It's incredibly useful and incredibly powerful. So how can we support it without exposing our users to the risk of a memory leak? Well, just as we solve problems in calculus through a change of variable, we're going to solve this problem through a change of ownership. We're going to take ownership of the completion handlers and we're going to offload it. We're going to outsource it to something called a service. Services are built specifically to own completion handlers, and they are owned by an execution context. When the execution context lifetimes ends, it destroys all of the services. And in doing this, we break the cycle. We prevent this memory leak. We allow this ownership cycle to occur, but we make sure that there will never be an instance where our users walk off and inadvertently leak memory. So what does a service look like? This most basic of services, taken directly from the Asio documentation, demonstrates what they look like. They must publicly and unambiguously derive from stdnet execution context service. They must provide a member type alias key type, which is either an alias for the type itself or one of its base classes. This formulation is somewhat confusing at first, but it exists to support polymorphic hierarchies of services, which I will not discuss in this talk. Then services must be unireconstructible from a std.net execution context mutable L-value reference. The purpose for this will become clear in 2 slides. Then services must provide this nullary invocable shutdown function, which is virtual and which they override, which goes through and destroys all their managed objects, ends the lifetime of each and every contained completion handler. This is part of the 2-phase deinitialization of services. Now, a lot of people's ears prick up when you say 2-phase initialization or deinitialization, and it's widely derided as generally a bad practice. But it's necessary in this instance in order for us to resolve potential webs of ownership, which can become quite complicated and intractable. Allow me to discuss this through an example. Let's say you have an execution context which owns a socket and timer service. And those socket and timer services are referenced by a socket and a timer. Now, those socket and timer have some pending asynchronous operation with some completion handler they've suspended, which is therefore owned by the service. And in accordance with this formulation involving an ownership cycle we've been discussing, those completion handlers share ownership of a state, which in turn owns both of those I/O objects. Let's think about what would happen if the execution context went through its services and simply ended their lifetime as it shut down. It might decide to end the lifetime of the timer service first, which would of course end the lifetime of the timer completion handler, which would try to end the lifetime of the state, but the state's ownership is shared. And the socket completion handler still exists, and so the state's lifetime does not end, which leaves this timer lying around, which has a dangling reference to a timer service. Undefined behavior. Now let's imagine we're in the world of 2-phase deinitialization. Let's imagine that the shutdown method of the service exists. Rather than going through and simply destroying the associated services, the execution context calls shutdown on the timer service. This destroys the timer completion handler, which tries to destroy the state, which fails because the ownership is shared. But notably, while the timer's lifetime lives on, so does the timer service. And so that reference isn't dangling. There's no undefined behavior here. Then the execution context calls shutdown on the socket service. The socket service destroys its completion handler, which finally destroys the state. And then the timer and socket have their lifetime come to an end, but they can still go off in their destructor and use their services because the lifetime of their services persists. Only once shutdown has been called on each and every service and all the completion handlers are destroyed is the destructor of each and every service allowed to run, thereby untangling this complicated web. Which leaves just one question. How do we get at these services? They're owned by an execution context, but how? The networking TS provides a triplet of functions to address this. The first and simplest is use service. You provide it with the execution context and the service type, and it returns to you a service key type reference. Note this key type crops up again to support those polymorphic hierarchies, which I will not discuss in this talk. Note also that if use service fails to find the service, it will create one using that unary constructor that I discussed 2 slides ago. Now, maybe your service has some parameters you wish to provide to it. You wish to customize some of its behavior. In this case, you can use make service to call an arbitrary constructor on that service and associate it with the execution context, which opens up a pattern where you create an execution context, call make service to pre-establish custom configured services, and thereafter IO objects calling use service will get the customized version. Note that if make service cannot create the service, it throws an exception. The last function, which I'll hopefully just glaze over a bit, is has service, which is not very useful. In a single-threaded world, you should probably know whether or not your execution context has a service or not. And in a multi-threaded world, make service and use service are thread safe, so a call to them might happen right after the return from has service. So if you predicate the call to make service on the return value of has service, you have a time of check to time of use problem. And indeed, I've never actually observed or written a single call to has service. Now that we understand all this machinery, let's go off and take a look at the service that we're going to use to solve our ownership problems, that we're going to use to untangle the ownership cycle that I discussed earlier. It, of course, publicly and unambiguously derives from StudNet execution context service. And it has a key type, which is simply its own type. There is no polymorphic hierarchy of services involved here. It has the obligatory unary constructor, and it has the obligatory shutdown function. This shutdown function not only destroys all owned completion handlers, all owned objects, all owned Ts, but it also causes future calls to destroy to be no ops. In this way, when those remaining IO objects, which we discussed with that diagram earlier, go off and try to use this service in their destructor, they might pass in a dangling pointer to be destroyed. Nothing will happen. The pointer will be ignored, and so there will be no undefined behavior, because the service will already shut down. It will know that object's lifetime has come to an end and it has no work to do. Which leaves just one function, and that's the create function, which we use to construct an object whose ownership is offloaded to the service, is offloaded transitively to the execution context, which is free from the ownership cycle we've been hand-wringing about. Now, just as with the pending class template I presented earlier, I've elided the actual implementation of this class. If you want to take a look at how it's implemented, you can go to the code associated with this talk, and there's a fully worked and tested example of it. Armed with this facility, we're now going to go back to our example and we're going to upgrade it so it supports that ownership cycle, so it doesn't succumb to a memory leak when we use that altogether too common pattern in the networking TS. The first thing we're going to do is we're going to add 2 type aliases to reduce the amount of typing that we're going to have to do and make this example less visually complicated. Then we add a completely new member to our basic async event, a reference to a type, our service type. This is the service that we're going to get our pendings array from and later release it to. Then notice that to support this offloaded ownership model, we've upgraded the pendings array from an array, actually resident in the IO object, to a pointer to an array, since its ownership is now offloaded to the service. You'll notice that our constructor has gotten a bit more complicated. We still take in that executor and we still use it to populate our executor member. But now we need to go off and grab a reference to our service. The way we're going to do this is we're going to make use of that use service function that I discussed earlier. We're going to call it and provide as its template parameter our service type. And then we also need to provide a reference to the execution context that service will be associated with. But how do we get that reference? In previous years, in the old networking TS conception of executors, executors were obligated to have a nullery invocable member function, a getter, which returned a reference to their associated execution context. But we're now in the brave new world of P0443, where there's no such requirement on executors. And so we introduce a new operation. We introduce a new property. An operation that is not concept preserving as prefer and require, but instead which can be used to retrieve heterogeneous values associated with a property. In this instance, we wish to query the stood execution context property of the executor. This will return to us a reference to the underlying execution context, which we can turn around and pass to use service, which will then return a reference to the service, which we can use to populate our member reference. The only thing this leaves to do then is to initialize our pointer, which we're going to do by calling create on the service to get back a pointer to a pending vector whose ownership has been offloaded to that same service. Now, this offloaded membership model is clearly manual management of lifetimes, and therefore we're going to need a destructor. And so we implement one which simply goes off to the service and calls destroy and provides the pendings pointer. Note that if we're being destroyed in response to shutting down services, all we do is take this pointer and pass it in. The service has already been shut down, and so it will simply disregard the call to destroy as a no-op. There will be no use of that invalid pointer, undefined behavior. The only thing that remains is to go through the rest of the implementation of our IO object and change a bunch of dots to arrows, because we've changed one of our members from being an actual value that lives inside the object to being a pointer whose lifetime is managed elsewhere. I will save you that process. After these upgrades, our IO object works. If you go to that code associated with this talk, this example is there. It has unit tests. One of the unit tests actually creates that ownership cycle we discussed, ensures the asynchronous operation doesn't complete and thus have the cycle broken by the pending object, and then lets everything go out of scope and asserts that everything is cleaned up. And those unit tests pass. And so now we support this use pattern from the networking TS. We support our users having this very obvious, very natural ownership model. So we must be done, right? All the ergonomics and guarantees of the networking TS must be satisfied, right? Well, no. Because we need to look more closely at the execution context we're using. We're using them to execute our final completion handlers. And when there's a final completion handler awaiting invocation, clearly the execution context has work to do. Clearly there's some reason for it to maintain whatever compute resources it manages, to keep them available to flush out that queue of invocable objects. But what happens when there is no work to do? What happens when there's no function objects awaiting invocation in the execution context? What should the execution context do with its computational resources then? Should it maintain them in the hopes that someone will submit some work in the near future? Or should it allow them to go away? The execution context which ships with the networking TS and which we use most often, stood net IO context, answers this question by saying that if there's no pending work to do, you should surrender the computational resources back to where you got them from. Its so-called run functions, run one, pull, and pull one, will return control of the calling thread to the caller if they ever run out of work, if there's no pending function objects. But one of the definitional things we do that we've been going over this entire talk is we don't submit function objects. We hold them back. We suspend them and only submit them later. What happens if in the interim, the execution context to which we wanted to submit them runs out of work? What happens if it releases those computational resources that we were depending on? What happens if that call to run returns? We could simply demand that the user of the IO context, the person who's running it directly, call it in some kind of loop. But that's not very ergonomic, is it? Now the user needs to have some kind of manual tracking regarding when and where and how and why all their operations have or haven't completed, and if they can move on with their lives or not. We don't want that. We want to enable this pattern where users can create an execution context, start a bunch of work, call run, and then when run returns, all the work is good and truly done. It's actually finished. They can move on with their lives. And so what we need is some way of tracking outstanding work. What we need to do is establish the outstanding work.tracked property on our executor. When this property is established on an executor, that executor is transformed. Rather than just being a handle to the underlying execution context, it is both a handle to the underlying execution context and a handle to the idea of outstanding work in the underlying execution context. Its lifetime becomes a signal to the execution context that there is work forthcoming, that it should keep its computational resources available, that we're going to need it in the near future. Until that executor's lifetime ends, therefore, the execution context will, if it's a stdnet IO context, not allow its run functions to return. It will not indicate that it is stopped. And therefore, when our asynchronous operation finally completes, assuming we keep such an executor's lifetime alive, we'll have those compute resources to turn around and use. We'll be able to invoke the final completion handler and report that our operation is done. We'll be able to enable this use pattern, where users set up all their work and call run, and when run returns, they know they're finished. They don't need to implement any manual checking or management. So is that all there is to it? Do we just need to go back to our example and carry around this one executor with this property established? Or is there more to it than that? Do asynchronous operations have just one executor, or is there more? Because while there's definitely the user's associated executor, there's also another executor that enters in play that brings in a definition of IO object I articulated earlier in the talk. IO objects are perhaps defined by the ability to call get executor on them and get back an executor. And this may not be the same executor as the one the user has associated with their completion handler, because this is the so-called IO executor. This is the second executor that enters into the fray whenever you kick off an asynchronous operation. It's called out by name in the TS. It's called IO executor. And it's also the executor that is to be provided as the default candidate object when you are deriving the user's associated executor using associated executor machinery. Recall that earlier when we called get associated executor, we not only passed the user's completion handler, but we also passed our IO executor. We passed the executor we'd return if get executor was called on our IO object. And so every asynchronous operation involves not just one, but two executors, an associated executor and an IO executor. And our users may have some expectation that when they awaken, when their asynchronous operation completes, that not just the associated executor is available for their use. They may expect that they can turn around and use this IO executor. They may expect that it's still in play. And so we need to maintain work on it for this reason. But there's another deeper reason, because IO objects may have another deeper relationship with their underlying execution context. Because IO objects may require some operating system specific functionality in order to project the asynchronous operations they implement. Consider, for example, that to implement a socket, you might need a completion port, an ePOL-FD, an IOU ring, or a KQ file descriptor. And who is going to keep those serviced? When your work is off running in the background, who is going to be paying attention to see if it actually completes? The logical answer to this is that you may have and require a special execution context which does exactly this. You may not care about submitting function objects to it. Instead, maybe you just care that it keeps that ePOL-FD serviced. It keeps dequeuing those notifications. But if you allow it to run out of work, if you allow it to release its computational resources, then no one's going to be paying attention to that ePOL-FD. You're never going to get a context when your write or read or connect is done. The user's asynchronous work may inexplicably stall out. And therefore, for this reason also, it's imperative that we maintain outstanding work.tracked on the IO executor along with the user's associated executor. So let's take a look and see how we might do that. Let's go back to our example and examine how we can modify it to satisfy this last requirement of the networking TS. How we can make our code more ergonomic and integrate better in the environment the networking TS provides. The first change we're going to make is that we need to grab our IO executor and try and establish outstanding work.tracked on it. And so that's the new first line of our initiation function. Note that we use prefer and not require. And the reason we do this is identical to the reason we used prefer and not require when we were trying to establish the allocator property. The underlying execution context might not have the concept of tracked work. It might never end. It might not have the concept of ending, and therefore it might not support this property. We don't want to upgrade failure to establish this property from just not establishing the property to a hard compile failure by moving from prefer to require, and therefore we're going to use prefer. Then we grab the user's associated executor by providing the completion handler and the default candidate object, RIO executor. But that's not enough. It's not enough to just get the associated executor. We need to try and establish outstanding work.tracked on it as well. And so we turn around and we do exactly that. Then, with both these executors that both track work in hand, we emplace into the pendings array. We emplace a lambda which captures the completion handler and both the executors, thereby ensuring that their lifetimes persist and that the concept of outstanding work in those underlying execution contexts persists. Moving inside the lambda that we emplace into the pendings array, we still go off and we grab that associated allocator, the one associated with the user's final completion handler. And we still try and establish the allocator property on the user's associated executor. But keep in mind, this isn't just the user's associated executor. This is a version of the user's associated executor which may have outstanding work.tracked established. And therefore, after this call to prefer, it may have both outstanding work.tracked and allocator established. With this in hand, we can submit work through std execution execute. But keep in mind, before we just submitted the user's final completion handler, we just passed the completion handler itself as the second argument. But now we can't do this because execute might put the user's completion handler to sleep. It might defer the invocation of it. And if that happens, we don't want our IO executor to run out of work and stall out. We want to keep it available for the user to use when their completion handler is invoked. And so rather than submitting the raw completion handler, we submit a lambda, which captures the handler and also captures the version of the IO executor with outstanding work.tracked established. Then, when the underlying execution context gets around to finally invoking our function object, we move the IO executor out of the lambda onto the local stack to make sure that its lifetime, and thus the concept of tracked work in the associated execution context, ends in a timely manner. And then we invoke the completion handler. We complete the user's asynchronous operation. We're done. Note that there's no need to carry along that version of the user's associated executor with outstanding work.tracked anymore because we submitted an actual function object for invocation in its execution context. And an actual pending function object was the original formulation of pending work that we established several slides ago. And therefore, it's fine to let that executor go out of scope, but we do need to maintain the IO executor. So now that we've bootstrapped this from nothing, now that we've added entirely new asynchronous functionality to the networking TS, what are the takeaways? Well, the first takeaway is that there's a lot of nuance and sharp edges, a lot of moving parts to building asynchronous functionality from the ground up, to establishing all the guarantees and practices of the networking TS. And so while this is a valuable tool in your toolbox, and you should certainly use it when appropriate, you should avoid it if you can. Your life will be easier and less fraught with bugs. If you can get the functionality you want through a composed asynchronous operation, then maybe you should do that. But you now have the tools to turn around and bootstrap asynchronous functionality from nothing. The next thing we explored was this common ownership pattern, this potentially cyclic ownership pattern wherein completion handlers transitively own their associated IO objects. And we learned how services fit into the ecosystem of the networking TS to break this cycle and enable this use pattern, to make sure that we don't arbitrarily close our users off from very valuable tools in their toolboxes. And the last thing we learned was how we can put that final sheen on top of the patterns and practices of the networking TS. How we can let execution contexts know that they might have submitted function objects coming in the future. How we can indicate to them that there's outstanding work and that they should keep their computational resources available. And in so doing, we provide our users with a wonderful, consistent pattern that they can call run on an IO context, and when it returns, know that all their work is done. That all they need to get their asynchronous environment bootstrapped is to create an execution context, an IO context, to start some work and call run, knowing that under the covers, in accordance with the patterns, practices, and guarantees of the networking TS, we'll keep that execution context informed of all outstanding work until everything is good and truly done. That when they return from run, they can move on, resting easy, because when widening the base of the networking TS, we were very careful to write our application honoring all the requirements and practices, keeping it as ergonomic as possible, keeping it as consistent as possible. And indeed, when establishing the baseline for asynchronous I/O in ISO standard C++, we should demand nothing less. And now I have a few minutes to try and answer some of your Q&As. So let's take a look there. Yeah, so the first one that I see here is a question about COVID-19. And there's been discussion about whether COVID-19 and the fact that the committee's been working remotely is going to affect the delivery of executors and networking. But those are both very, very high priority. Like the paper, I think it's P0592, that lays out the broad plan for C++23. Basically, executors, networking, and coroutine support are the highest priority. And so I haven't heard anyone say that it's not going to get in or they think it's not going to get in. But what I have heard is people who are kind of like, are we going to be able to do everything, or are we just going to get networking and executors? So, I mean, we do have a solid year and a half to try and wrap that up. And there's been a lot of discussion about executors over the summer and moving into the fall. We're looking to start actually polling that. And so hopefully then we can move on to networking and actually deliver despite the fact that COVID-19 happened. I didn't actually see the talk before mine. So yeah, I didn't see the efficient implementation of a move only callable. And I'm sure that the example that I'm going to upload in the zip, the repo associated with this slide, could be improved. It's just something that I wrote that works, that's mostly slideware. I mean, I do use it at work, but the place that it's used at work is not efficiency critical. And so I didn't put a lot of time into implementing it. The inheritance from service is necessary, as you know. I would guess the inheritance from service is necessary for that shutdown virtual method. I mean, it's likely, it's probable that you could implement it by using a concept and type erasure, but then it's like kind of you're back at square one, right? Like you're still implementing a hierarchy of virtual functions on top of it, so you may as well punt that onto the user. Interestingly enough, when SG4 networking reviewed the networking TS, one of the things that was pointed out was that it's kind of weird that we have a concept called service that requires public and unambiguous derivation from another type. Like that was pointed out as weird in, and there's a prog meeting actually in February, the last time that we were allowed to look at each other in person. I actually don't expect any problems with IOU ring. That's the next question, is about IOU ring. I don't expect any problems with IOU ring because I've actually written a toy implementation of an executor execution context and IO object that use IOU ring, and it worked very well. I mean, I didn't try and completely tune it, but it works, and the code is on GitHub, and I actually have an outstanding issue to address with that. That looks like all the questions, and I think we're right on time, so I'm going to wrap up there. If I'm around in the hallway, just feel free to talk to me about this.